So welcome everyone. I understood these last days that you cannot wait for seeing examples of application of topological data analysis. So we will start, I modified the program a little bit. We will start this tutorial by studying some examples, some recent examples where people that we will first study some examples where doing topology in data analysis is a good idea. And okay, I put this picture in the introduction of this book of Steve Udo 6 years ago. So this is a nice, very nice introduction to persistent homology. And in the introduction, there is this page where Steve lists a lot of recent areas where persistent homology have been applied. So you can see image analysis, chemistry, robotics, medicine, a lot of stuff. This is really interesting, and so I selected today three papers, three examples of applications that I really like, and I hope you will see how topology can be useful. Then I will introduce a notion that is called Betty curve that we'll use at the end in the tutorial. So I have three examples of applications for you. Warning, I am absolutely not a specialist of chemistry and medicine, so neither image analysis. I just read these papers, and so I'm gonna explain to you what I understood. If some of you are specialists and want to clarify things, don't hesitate. So this first data set, so this is chemistry. The authors study a very important, well-known molecule that is called cyclooctane. It has 8 atoms of carbon and 16 of hydrogen. And what is, so it looks like that. We have like a crown of a ring of carbons and then hydrogens. What is interesting is that this molecule admits several spatial configurations. It is not rigid, okay? You can see that the hydrogen atoms may move a little bit, okay? There is a freedom in this molecule, okay? Of course, because of the physical interactions between these atoms, all the configurations are not allowed, all right? There is only some configurations that the molecule can have, and physicists described these different configurations. You have, for instance, here the crown configuration, the both chair configuration, but there are many, many more. And an important question is to understand the dynamic of this configuration. How can one molecule transform in another one? Okay. And in order to understand that, let me show you what they did. They transformed each of these molecules into a point in R to the 72. So how do we do that? You take a molecule in nature, okay, a cyclooctane molecule, and so you have 24 atoms, and you will look at the coordinates of each of its atoms, okay? You center the molecule at the origin, and you look at the coordinates. You have 3 coordinates per atom. So at the end, you have 3 times 24 coordinates that describe the spatial arrangement of the molecule. Okay. So, given a molecule, I can transform it into a point in R to the 72. And so what do? They simulate a lot of these molecules, and they obtain a lot of points in R to the 72. And so this is a point cloud, and we can try to understand how it looks like. We can try to understand its topology. Okay? And it turns out that this point cloud has a very interesting topology. It has a two-dimensional topology, and it can be described as the intersection, the union, sorry, between a sphere, a two-dimensional sphere, and a Klein bottle. Okay, and they intersect in two rings. So this is very interesting. You can even try to understand the areas of these subsets. In the Klein bottle, you can find I think the Botcher configurations. In the sphere, the Cron configurations. Okay, and molecules evolve as you walk on this shape, and this gives a very interesting insights about how this cyclooctane molecule behave. Okay. The second example comes from image analysis. So one important question in image analysis is to understand the global behavior of natural images. A natural image is not an image of nature. It's just a photograph, an image you can take in real life. Okay. For instance, this is a photograph. Okay, so this is a natural image. And the idea will be to understand the sets of whole natural images. Okay, this will be interesting to develop algorithm. Though this is very complicated. What they do here, the authors only extract little patches of natural images, 3 pixels by 3 pixels. Lucas asks, what these people are using to compute the simplicial complex? They used check or rips. They don't use neither the check or the rips. They use another algorithm. I think it is called EMAp. Oh, because here we really want to obtain something which has which is homomorphic to the space of configurations. We do not want only a simplicial complex that has that is homotopic equivalent. So this is a more complicated algorithm, but I think at first in this study they just try to compute the Betti numbers of these shapes, and then they observe that okay, this could be this thing, and then they use the more sophisticated algorithm to understand, to triangulate the space. Really have a look at the papers. It is really nice to read. So natural images, we take, so we have a large set of natural images, and the authors extract some patches. Okay. We will do the same thing. We will transform a patch into a point in some Euclidean space. And a patch is 9 pixels. We have a gray value. So each patch can be converted in a point in R to the 9. Okay. And same strategy, we will generate a lot of patches and obtain a point cloud in R to the 9. And we'll try to understand its topology. And it turns out that this topology also is a two-dimensional object, and this is a claim bottle. The set of patches is close to a claim bottle. So here, what they do is first they use a Rips complex or something a bit better than the Rips complex, because the Rips complex is a bit sensitive to outliers and anomalous points. And we have some anomalous points here. So they use kind of a Rips complex to obtain the homology. And when they read the homology, they see 1, 2, 1. They see the homology of a claim bottle. But if you see the homology of the claim bottle, that doesn't mean that you have a claim bottle. In a second step, they find an embedding of the claim bottle such that the patches are really close to this claim bottle. So you can say that the underlying space is a claim bottle. And yeah, and this is there has been a lot of applications, some applications of that. Daniel, is dataset a popular one? The set of natural images that they use, I don't know. But you can have a look at the paper. It's nice to read. yeah, this is a nice example. And a last example, Pumi says, concluding that the data behave like a claim bottle is a main objective of the paper. Yeah, in this paper, they just want to understand the topology of the patches. This is really the starting point of this analysis. And then once you know that, you can try to develop interesting stuff about that. Because as it is, it's only a theoretical knowledge, right? Okay, the last example is in biomedicine. This is a bit different from the others, but the idea is the same. We want to understand the topology of here a disease, breast cancer. So breast cancer, we have patients, women, and in order to apply the same method, we have to transform a woman into a point, right? And what they do is that they extract genomic variables. So I couldn't say a lot about that because they extract genomic variables, and then there is a lot of pre-processing to obtain a nice representation of a patient. What they get at the end is 262 coordinates. Okay, and they will study a lot of patients and obtain a point cloud in R to the 262, right? Here we will try to understand not the topology, but the geometry of this data set, because it turns out that it's some kind of a tree, right? And topologically, a tree is a point, so this is not very interesting. So they use another algorithm here. I wrote in the chat. It's called mapper. And this algorithm allows to understand the graph structure of your datasets. Okay. And they observe that we can describe this graph with 3 distinct branches. Okay, it seems like the breast cancer disease, the patients lie on something which was like a tree with 3 branches. And you can try to understand the different branches, okay, because the branches cluster people. And by analyzing this graph, they discovered something very interesting. They discovered a type of breast cancer that was not known before, that they called CMYB+. And so these patients, they produce a special protein, and it turns out that they do not die from breast cancer, and they do not have metastasis. Okay, this is a new class of breast cancer that they discovered by analyzing this topology. I see two questions. Gabriel asks, Gunnar Carlson is an important name in the field. Yeah, he was one of the first ones to both develop the theory and the applications of all of this. And Pumi says, do they use the results to classify the type of breast cancer given a new observation? I don't know. I don't think they do in this paper, but maybe there has been some works after that. Could be interesting to see that. Yeah, of course, in principle, you can do that, because once you convert someone into a tuple of coordinates, you just look what cluster it is the more close to, where the patient lies on this topology, on these subsets, and you can estimate, you can make inference about what cancer they have. Okay. So we will do a bit of that this afternoon in the tutorial, though we don't have persistent homology yet, right? This is for next week. So I'm a bit frustrated that we do not have persistent homology yet. I will give you a new tool, though, for today. This is called Betty curves. So let's do some math again. Maybe I should remind you a bit what we saw yesterday. We studied the problem of topological inference, in particular homology inference, right? The problem was presented like that. There exists a subset, an unknown subset of the Euclidean space that you observe via a finite sample, okay? It can be the finite sample that you observe X may be a subset of M, or maybe not. It only has to be close enough to M in a Hausdorff distance, as we've seen. And the question is, estimate the homology groups of M, estimate the Betty numbers of M from the observation X. And we've seen that a nice strategy here is to consider the thickenings of my set X, right? The thickenings can be written as a union of balls. And we saw how to compute the homology of union of balls by using the check complex, which is the nerve of this cover, or by using the Rips complex, which is the clique complex of the neighborhood graph, or the clique complex of the one skeleton of the check. Okay. And we ended up with a lot of different complexes who may have different topologies, different homologies, right? So at the beginning, we always have something not very interesting. We only have a discrete topological space whose Betty numbers are the number of connected components in 0 and 0 for the other. And then we get closer and closer to the actual underlying shape. And at some point, we grab M. and we have the homology of the underlying subsets. Okay. And I told you that selecting these values of T is doable in theory, but in practice, you cannot apply the theorems of yesterday. So the real solution to that is persistent homology. But for the moment, we will consider Betti curves. The Betti curve, the ith Betti curve, is the following map from the non-negative real numbers to n that maps any t to the ith Betti number of the t thickening of x. Okay. And in our experiments today, we will consider the RIPS version of the Betti curve. So this is a map that assigns to any t the ith Betti number of the RIPS complex of the t thickening, the t RIPS complex of x. And okay, and so this is a small exercise for you. The 0th Betti curve always is non-increasing. Okay, your 0th Betti curve is something decreasing like that. Okay, because the connected components can only gather when the parameter t grows. Okay. This is it. So let's go to the tutorial. Clear. This is the link. Yeah, Lucas. It is. There is some value from which it is equal to 1. And you can give some bounds on this value. So this is a tutorial that we will do together. Yeah, I will give you the link. There is also some files to download. The problem is that they are very heavy, these files. I hope you will be able to download them. Well, yeah. And the files. All right, so if you go into my GitHub, in the folder EMAp, you can find the tutorial 2. This is a Jupyter notebook. And then in this folder here, tutorial 2, there is a lot of files. If they are, I will upload some zip versions of them. Okay. So what you can do first is simply download the notebook. We will read the first part of the notebook together, and then I will give you some time to do the exercises. Does anyone have any problem with downloading the notebook? Tell me when you are able to open the notebook. Okay, should we start or does someone need help? Okay, let's go. So in the first part that we will do together, it's only a synthetic data that we will sample and then analyze them. And the two last exercises, we will study real data. So I start by importing the libraries. This is a cell that contains the functions of the last tutorial, and I give you new functions for today. There are 5 of them. So this may be a bit obscure for you right now, but next week you will be able to code all of that by yourself. Okay, it uses the Goody library. So I like to take this example of the circle because it is the most simple example you can use. First, I sample some points on the circle. Okay, there is this function sample on circle. It gives you an NumPy array. Okay, you have 50 points in the plane, 2 coordinates. You can compute this cell to see how it looks like. I just plot the dataset with matplotlib. Okay, so we have 50 points drawn at random on the circle. So if I compile again, I will obtain new points. I want to compute the homology of the Rips complex of this data set. I want to compute the thickening and then the Rips complex and see its homology. And this is written here. So I select a value of thickening, T, and then I will build my Rips complex. Okay. So I write, I create a simplex tree. The simplex tree is a goodie version of a simplicial complex. And as we did last week, we insert the vertices one by one. Okay. The points go from 0 to 49. And then I add the one simplices in my graph. So remember that in the Rips complex, you add an edge, Ig, if the distance between the point, the ith point and the jth point is lower than 2 times t. Okay? And in order to compute the distance, the Euclidean distance, here I use an NumPy. But you can simply use the algebraic formula for that. Okay. So here, until here, I just created the Rips, the graph, the neighborhood graph. The Rips complex, it is the clique complex of this graph. And in Goody, this is called the expansion. Okay. Expansion equal clique complex. So when I say expansion 2, I will add the simplices of the clique complex up to dimension 2. Okay, I do not add the 3 simplices that comes from 4 cliques or the higher dimensional ones, because this is a lot to compute, right? Up. Here I created my Rips complex, expanded until dimension 2, and then I carried its Betti numbers. So I give you this function here, Betti numbers. If I compile that, I obtain that the Betti numbers of my Rips complex are beta 0 equal to 10 and beta 1 equal to 0. And we will verify that. Plot thickening is a function that draw your thickening. Okay, I wrote that in matplotlib. So this is the T thickening with T equal to 0, 1. So we will verify that we have these Betti numbers. So beta 0 equal to 10 means that we have 10 connected components. So I will count them. 1 here, 2, 3, 4, 5, 6, 7, 8, 9, and here they are not connected, 10. So I can see that my beta 0 is 10. And is my beta 1 0? Yes, because there is no cycle in here. Okay, this is not a circle yet. So let's try with a higher value of t. T equals to 0, 4. Same thing. I add the vertices, the edges. So I add more edges here. Then I expand my graph to obtain my Rips complex. And I plot the Betti numbers and the thickening. And this is a circle, right? And as it is a circle, it has the Betti numbers of the circle, that is 1 and 1. Okay, you can try with any value of thickening. If you go too far, you will obtain a big ball, right? When t equals to 1, all the balls intersect and you obtain a simplicial complex that a thickening that has the homotopy type of a point, as you can read here. Okay, let me show you now how Betti curves look like. So the Betti curve is simply the curve that tell you at each value of t what is the Betti number of your t thickening, here of your Rips complex. So this function, I give you get Betti curves from point cloud. There is two arguments. The first one is your point cloud, x, and the second one is an array of floats that represents the values at which you want to compute the Betti curves. So I take here for an interval the linear space between 0 and 1. So this is the NumPy function. I take 100 values between 0 and 1. Okay. And so first, I will compile that. Up. I have my Betti curves. The Betti curves, I have 4 of them because my simplicial complex. All right, so it computed Betti curves up to dimension 4. And each Betti curve has 100 points. Okay, so I can plot them. This is the 0 Betti curve. And as you can see, it starts at 50, because when t equals to 0, we have 50 connected components. And then it decreases until the value 1. So here, that should be the moment where we only have one connected component. This is strange. Let me see how the first Betti curve looked like. So this is the first Betti curve. As you can see, it is equal to 0 until some value where it goes to 1. Then it is 1 until here, and it becomes 0. Okay, so this is a bit strange because at this value here, between 0 and 0.2, we should have one connected component, but this is not the case. If I take t equals to 0.15,
I think it's 1 there, but the scale is a bit smaller there. It's slightly above the x-axis there.
Yeah, really? No, actually, I think this is it, because you have one connected component before having a circle, as you can see here. This is for 0.15. I have only one connected component. And if I go a bit above, this is a circle here. By the way, the data you observe on your notebooks should be different than mine, right? Because this is a random sample of the circle. Okay, so in this Betti curve, we are able to read, to infer at which point my thickenings become a circle. Yeah, and the fact that it becomes trivial, the fact that the Betti curve becomes 0 before 1. For instance, if I were to take 0.1, 0.9 here, So as you can see, my thickening is still a circle, but the Betti numbers are not the Betti numbers of a circle. So you may think that this is a mistake. It is not, because we do not compute the homology of the thickening, but of the Rips complex. And remember that the Rips complex may not have the homotopy type of the thickening. The Rips complex is a clique complex. And so basically for this value, 0.9, the Rips complex already have the inner triangle here. Okay. Okay. A remark in Goody. So here I built the Rips complexes by adding vertices, edges, and then expanding. But in Goody, you can do it in one line, in two lines, actually. You first define this structure, which is called a Rips complex in Goody. And from this structure, you create a simplex tree. This gives you the Rips complex from your point cloud. Okay. Now I would like to do the same experiment with a noisy sample of the circle. So you have this function, sample on circle. The second argument, SD up, is a parameter that so you basically you add noise to every point. Okay, and this is a Gaussian noise, and the standard deviation of this Gaussian noise is SD. So I took here 0.1, but if you were to take higher values, you will obtain less nice point clouds. Let's take 0.1. I will do the same. Take the value 0.2, build the Rips complex, and then compute its Betti numbers. All right, so here we have 3 connected components and no cycles yet. What if we take a higher value, 5? Okay, I still have a circle. This corresponds to the hypothesis of the theorems we saw yesterday. Even if the point cloud is not sampled on the circle, while it is close enough, we can hope to recover the underlying space with thickenings. Yeah. And notice that this is a special kind of noise. We cannot have an anomalous point everywhere. This is just some little noise in the coordinates. Okay, Betti curves. Up, I compute them. And this is how they look like. Pretty close to the one we've seen before. Betti 0 is decreasing until 0.2, where we have only one connected component. And the one Betti curve becomes 1 at some point and then becomes 0 again. And unfortunately, I wanted to show you a phenomenon here, but this does not show. So I will do the same experiment again with another point cloud. Up. Okay. Nice. So this is my new point cloud. And as you can see, the one Betti curve shows something interesting. Between around 0.1, it becomes 1 at some point. Okay? So what happens? I will go here. If I take 0.1, I should have a one cycle, but look here. You have 4 points. I will go a little bit more than 0, 1. Yeah. Can you see that? These 4 points, they form a circle. They created a cycle. Okay? This is why I have a beta 1 here equal to 1, though I do not even have a circle globally. This could be called topological noise. Okay? Fortunately, topological noise disappears fast, right? If I take 12 up, it disappeared. So one must be careful when analyzing Betty curves, right? But so yeah, this is actually really a problem, because if you had a lot of topological noise like that, you could obtain a Betty curve here, which is never 0. And you could say, yeah, well, I have a circle, of course, because it's 1 most of the time. But this could be because of a lot of topological noise, right? So this is a problem with Betty curves that will be totally solved by persistent homology, though I won't present that today. And Marcio says we should look for stable topological configurations. In practice, there will always be some topological noise. This is why Betty curve is not very powerful in this context. All right. So I have an exercise for you. The first one, in this cell, I gave you a data set. It's 200 points in R4. Okay. I give you the information that this is sampled on a 2-dimensional object that you may know. And the question is, can you recognize which object it is? So what you have to do is to compute the Rips complex, look at its Betty curve, and guess the topology of it. Okay. Compute the Betty curve only on 0, 1, because this will be expensive if you go too far. So I'll let you 5 to 10 minutes, and I'm here for any question meanwhile. Okay, I will propose a correction. So we just have to compute the Betty curve of this data set and see what happens. So what is the function? This. Can I use data here? No, okay. I have to convert my dictionary into an NP array. How do I do that? X is data I, something like that. Oh yeah, the solution of Lucas is even better. Up, Betty curves. This is so slow. Okay. Now let's see how they look like. Okay. What I can observe from the first Betty curve, the 0th Betty curve, is the same thing than usual. It should go to 1. In order to see that, I will plot between 0 and 5. Okay, just to see that it stabilizes to 1. Okay. Now let us interpret the first Betty curve. So Lucas says that it's infractal, and another Lucas says that I get a Betty 1 between 19 and 12, 20. Actually, all of this here is topological noise. The real information in this Betty curve is when it stabilizes, okay? When you arrive in the interval where you have the homotopy type of the underlying object. And this is here, okay? This value being equal to 2. I can plot it between 0 and 5 to see what happens. Yeah, it goes up, then it goes down and stabilizes at 2. Okay. So this may be a bit strange for you, but Betty curves are hard to interpret. Okay. This will be way easier next week with persistent homology. But I said that it's a 2-dimensional object, so I should also look at its 2 Betty curve. And its 2 Betty curve. What is it? Okay. Seems like it stabilizes here, and then, well, we have topological noise again that you are not able to recognize yet. So I will zoom. Yeah, this is one. So now I can propose inference. Yeah, exactly. We have up beta 0 seems to be equal to 1. Beta 1 seems to be equal to 2. And beta 2 seems to be 1. This is because of this area, and this area. 1, 2, and 1. So this is my proposition. This is my estimation. The Betti numbers are 1, 2, 1. Now I can look at the list of all the shapes I know. And it turns out that this is the homology of the torus. Okay? The homology of the torus is 1, 2, and 1. This is not a double torus. The torus, the simple torus, the empty torus, right, has two beta 1 equal to 2. Because in the torus, some people said that it has only one cycle, but no, there is 2 cycles. There is. So if you take, do I have a torus somewhere? No. I will do a drawing. So up, this is a torus. You have a first hole here. Yeah, that's it. And you also have a hole which goes like that. So this is the homology of the torus. We could try to infer that our underlying shape is a torus, but there is a problem. There exists other shapes that have this homology, even other 2-dimensional shapes. And for instance, the Klein bottle also admits this homology. The Klein bottle also has 1, 2, 1 as the first 3 Betti numbers. Okay. So Klein bottles. Can I draw the Klein bottle? You also have a cycle here and a large cycle that goes like that. So what I can say, I cannot conclude from this experiment. Is this a torus? Is this a Klein bottle? I don't know. If I want to understand more what happens here, I should use more sophisticated tools. We could check orientability, exactly. And you can check orientability by computing homology in other finite fields. And I will write that in the chat. We computed homology over Z over 2Z, right? This is what I taught you this week. We could have considered Z over 3Z. And over this finite field, the Klein bottle does not have this homology. And so what we should do, if I will change my function here, get Betti curves from point clouds. I will call that where is it? Yeah, I will create a new one. Get Betti curve from point cloud over Z3Z. And I will change a parameter in this function here, compute persistence, but over the coefficient field 3. Okay, I change a little thing here. Up, this is get Betty curves from point clouds over Z3Z. Up, and I do the same experiment. And at the end, we should observe still the same homology. If we still have 1, 2, 1, this is a good information that we have a torus, and this is the case, right? 1, 2, and 1. So yeah, my estimation is this is a torus, though this is not for sure, right? If we really want to be sure that this is a torus from a statistical point of view, we should really find an embedding, a triangulation of our space. Anibal, could we identify something like a Mobius strip from the Betti numbers or homologies? Yeah. If your surface, so you can show something in differential geometry. If you are not orientable, if your surface is not orientable, then there is a Mobius strip. And this has a consequence in homology. When you are not orientable, I will write that. When you are not orientable, up, your homology changes when you go from Z over to Z and Z over 3Z. And actually, the remark, the best theory of homology is over Z. But this is out of the scope of this summer course. The Mobius strip as a topological space is a circle. Yeah. So the Mobius strip in itself is topologically not something complicated. But actually, when you can put a Mobius strip, here we consider surfaces, right? So if you have a Mobius strip, it cannot be simply a strip, simply a band. It has to connect to itself. And so this is something you cannot retract. Yeah, I say the best theory of homology is over Z, because as Marcio says, there is a theorem called the universal coefficient theorem that allows to compute the homology over any field from simply the homology over Z. In other words, homology over Z contains all the homologies over the finite fields. Z, P, Z. And an interesting observation in persistent homology. So all what we did here is compute homology over Z over 2Z, but it could be the same for any other finite field. The definition will be the same, the theorems will be the same, the algorithm will be the same, but we cannot do the same with homology over Z. This is way more complicated. And this is something people try to do at the moment, defining persistent homology over Z. And this is very complicated algebra. Okay, a very interesting remark of Pumi. The 3-Betti curves of the data increases exponentially in 0, 1. So let me see it. Is this an ongoing problem? Z persistent homology. I say Z persistent homology is a very important problem. Actually, you can show that it is too difficult. Yeah, my 3-bit curve increases. What is that? Up 3. This is something that is a consequence of our algorithm. Actually, remember that here, get Betty curve from point clouds. If you look at the function I wrote, you compute the Ritz complex, and then you expand the Ritz complex until dimension dim, and dim is 3. Okay, meaning that I only add simplices up to dimension 3. But if I do not have the simplices of dimension 4, then all my then I cannot compute the homology in dimension 3, because homology in dimension 3 is the dimension of the cycles minus the dimension of the boundaries. And the boundaries are the boundaries of the 4-dimensional simplices. But I do not have 4-dimensional simplices here, because I only expanded the RIPs until dimension 3. Yeah, so if I simply changes this here, I would say dim equals to 4. This should be different. Yeah, exactly. And I will compute between 0 and 0.5, so this will go faster. Up. Okay, this is 0. Well, let's compute it over 0, 1. But yeah, this will be slower to compute because we have more simplices. So while this runs, if there is no other questions, I will describe the next exercise. Okay, so this is a very nice data set, exercise 45 from this university here. This is a collection of pictures of objects that turn on themselves. All right. For instance, so yeah, we have 20 objects, 5, 5, 5, 5. They are ordered. And for each of these objects, they took 72 pictures of them, okay, while they rotate. You subdivide the circle, the interval 0 to pi in 72, and you move them according to the angle. And what we will do here is trying to understand the topological space that consists in all the images of one object. I take one object. I have 72 pictures, right? Each picture can be converted in a point in R to the 128 times 128, because it has this many pixels. This is the same thing as what I show you in the beginning of the lesson with the analysis of natural images. For instance, this duck, I have 72 pictures of it, so I will obtain a point cloud of 72 point clouds, 72 points in R to the 128 times 128. And I want to understand the topology of this point cloud. So, oh yeah, I see that the computation finished. So this is my Betty curves when I expand until dimension 4. And as you can see now in the 3 Betty curve, this is 0. Just some noise at some point. Okay. So this is consistent. Okay, back to my pictures. What I want you to do is to compute the Betty curves of each of these objects. So the files actually weight, I think, something like 2 mega. So maybe do not download all of them, just 1 or 2. This will be enough. Put the file in a subfolder of the folder where you have the notebook. You should, yeah. Where is it? Okay, if you follow the link, you will find tutorial 2. This is a folder, and you have to download like some clouds. Okay, cloud 1 or cloud 2 or cloud 3. So these are the images of our objects. Yeah. Oh, 18. So once you have downloaded these files, you have this function which allows to open a data set in Python up. For instance, if I write matrix equal open dataset exercise 45 2, this will open the second point cloud. So let's say 1. Up. What is matrix? 70 files, 70 images with this many pixels. And I can plot them to see how it looks like. Yeah, this is my doc. So I would like you to answer this question. I'll let you 5 to 10 minutes. Then I will correct, and we will do the last exercise together at the end. All right. Have you been able to see something? Okay, I think you computed the Betty curves between 0 and 1, but you should go over 1 because the distance between the points is greater than 1. So the Ribs complex at time 1 is still disconnected. Okay, so I will start with this. Here, I only want up to dimension 2. And so I open to start the duck. And I compute the Betty curves. So if I were to do the same as you, oh, this is matrix. I will obtain now something very interesting. I have only disconnected points here. So let's go between 0 and, I don't know, 20. Okay, now this is interesting. When I want to read Betty curves, if I think that my underlying topological space is connected, I have to wait for it to be connected. Okay, so I have to wait here until 7.5. My Ribs complex becomes connected, and then I can read the higher dimensional homology. And what I see here is that seems to be 1. Looks like the homology is beta 0 equals to 1, and beta 1 equals to 1. And what is that? This is the homology of a circle. And actually, this makes a lot of sense because up. Well, what is it, this point cloud? Yeah, we could have guessed that, of course, because in R to the, I don't know, very high dimension, I have points, okay, that start at somewhere, goes around, and ends at the same point at the beginning, right? I have a connected dynamic here. If I want to, R to the n, and the parameterization is time. Yeah, I have a point cloud that looks like that. Up, 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 up. I don't know where it goes, but what I know is that at some point it will connect with the first one. So we have a one-dimensional subset, the parameterization one-dimensional, something which connects to itself at the end. So this is a circle. Oh, you can see the drawing. Can you see anything that I drew on my computer? I wrote the bit. Oh, Can you see if I write now? Cool. So we were in R to the N, and I have a point cloud here that starts somewhere up. You follow the time, you have 72 points, 72 pictures. And what you know is that at the end, the last image is the first image. So this is a connected one-dimensional object. This is a circle. If the duck spins in the vertical direction, will it be a torus? Very, very interesting. Yeah, you have to take care. You have to be careful that I think this will be a torus, but you have to, yeah, be careful of the symmetries of the duck. Before answering your question, let me show you another example. Okay, the question said, for instance, for I equal to 4. I equal to 4. What is it? My fourth object. Okay, this is the cat. Ciao, Ludmila. The cat, this is the same. I observe a circle, okay? I have 1 as a stabilized value of the Betty curve. Now, let's see 7. Okay, this is this piece of wood. I prefer the 10th object, I guess. Yeah. This is a box of Vaseline, okay? I equal to 10. See that? Now I do not observe 1 in the first Betty curve. It seems like it's around 2, right? Can someone explain why do we have 2 here? Yeah, I have some nice answers. Exactly. It crosses itself. The back and the front, actually the sides are similar, right? Here, up, and here, I have the same picture, barely the same picture because it's different at the top. The word Vaseline goes in the other direction. So, what is my point cloud? Can you see what I'm drawing right now? Okay, so I start here, up, I have some points, but then when I go to the other side, I am very close to the first point at the beginning, right? And then I continue up, and I end up again at the beginning. The beginning, the sides. I mean, if I start at the sides. So what I have is 2 circles. I have 2 cycles. Okay. And this is because of the symmetry of my objects. There is 2 pictures that are actually the same images, barely. So my topology, my space up there is a lemniscate. It's 8. It has 2 cycles. If you apply dimensionality reduction, yeah, you will see this easily. You can draw, yeah, take any algorithm of the dimensionality reduction, draw it in the space, and you will see 2 loops like that. Okay. So now a little question. Thiago says before, could you please run the 16th and 17th? So what is it? Yeah, so the second one looks like just the same image every time, and this one is this one also. So I think this won't be very interesting. Yeah, seems like the Betty curve, I mean, compared to the other ones, it's very stable. Maybe one or two. I don't want to say something here. And 17. Yeah, it's harder to interpret. Maybe you want to say one, or yeah. Instead, look at 13 and 20. No, let's say 13. Can you guess what topology I will obtain? One cycle or two cycles? One. Yeah. Seems to be, it should be one because we do not have any symmetries. What is it? 13. Oh, actually, I observe two here. So there should be actually some. Yeah, maybe the two sides actually look a bit similar. The distance between the two sides is small, and we should maybe have something like that. Not really the same, but still close here. Okay. So this is it for the images. And yeah, so well, what happens if, this was a question, now I consider two rotations. I guess this is a torus. But if you have symmetries, you would obtain torus that could cross itself, right? So you could observe interesting topologies. Okay, it's already, yeah, okay, it's late. So we'll just say a word about the last exercise. This is a very nice data set from this article here, where they use topological data analysis to analyze a protein, which is called the maltose binding protein. I quote the article here. And it turns out that there are two states of this protein, an open state, a closed state, and an open state. Okay. And so you can describe such a molecule with a point in R to the how much? R to the 370. Okay, basically you group atoms and you obtain 370 atoms, and then you convert any molecule, any protein, in a point in R to the 370 by looking at distance. Okay, so here, this is a different example. We do not embed the proteins in a Euclidean space. Excuse me, this is different. We will compute distances between proteins. Okay, and a very important thing is that when we thicken objects, they have to be embedded in the Euclidean space, right? When we thicken points. But the Ritz complex, to define it, you only have to have distances between your points. If I have an abstract set of points and distances between them, I can define the Rips complex. So this is interesting because even if your dataset is not embedded, you can still consider its topology, its abstract topology with the Rips complex. And this is what they do. So they obtain different Rips complexes for each protein. They have 7 closed proteins and 7 open ones. They compute they do not compute the Betty curves of the Rips complexes. They compute the persistent homology of the Rips complexes. And I wanted that to be the conclusion of today. We could have computed Betty curves of these proteins and trying to compare the Betty curves and see that Betty curves between closed proteins, one Betty curves, I consider one-dimensional Betty curves, are close to each other, while if you take a closed protein and an open protein, you will obtain different Betty curves. Meaning that thanks to Betty curves, we can compare these proteins. And this is very nice because it's very hard to guess if a protein is closed or open. Okay, but by looking at its topology in this funny way they did, you can cluster proteins. Okay, and yeah, actually the conclusion was that Betty curves here do not work very well. We should they actually use persistent homology in their paper. Okay, let me conclude. Oh, let's see what happens, Lucas, in 2 minutes. So I want. Okay, conclusion of today. Thank you, everyone. Again, this was very nice, very interactive. So I showed you some data sets in important papers of topological data analysis. We studied it a little bit in this tutorial. We've seen that you can find topology when the point cloud is embedded in the space, but even if we only have distances. We use Betty curves, and yeah, so Betty curves are a consequence of something that we are waiting for, I guess, persistent homology. So yeah, we will do that next week. I'm very excited. And well, I do not give you homeworks for next week. Thank you, everyone.
Rafael, can I ask you a quick question? Oh, no, I'm sorry, but Lucas had a question before me, I think.
Yeah, but I think this will last
take a
while with Lucas. So please ask your question.
So it's just